audible now for everyone?
Yes, sir.
Yes,
Yeah,
sir.
okay.
Yes, sir.
Yeah, okay, thank you very much. So, first I will recall what do you mean by singularity and poles, okay? And then I will start my lecture. So, let me recall. A point Z0 is said to be a singularity of a function f of z if the function is not analytic at Z0, but in a deleted neighborhood of Z0, okay, there exists at least one point at which the function is analytic. So such a point is called the singularity of f of z. Okay. So let me write the definition one more time. Hello. Yeah. So a single valued function f of z is said to have a singularity at z is equals to z0 if f is not analytic at z0, okay, while every deleted neighborhood of z0 contains at least one point at which the function is analytic. So one such example is if you take f of z is equals to 1 by z into z minus 1. This function is not analytic at z is equals to 0 and z is equals to 1. Okay. Therefore, if you draw the picture, this is 1 and 2. This function is not analytic at origin, but you can find out a deleted neighborhood of origin. Okay. So the function is analytic. At least one point you can find out the function is analytic. Similarly, if you take 1, you can always find out a deleted neighborhood of 1 at which the function is analytic. Okay. Therefore, z is equals to 0 and z is equals to 1 are the singularities of f of z. Okay. If we take the function f of z is equals to, say, f2 of z is equals to z bar. Okay. The function f of z is equals to z bar is nowhere analytic. Okay. Is nowhere analytic. So, do I mean that all the points in C are the singularities of z bar? Do I mean that all the points in C are the singularities of z bar? So suppose, yeah, very good. So if I take any point z0 and whatever the small deleted neighborhood of z0 if I take, it is not analytic in any neighborhood of z0. Therefore, we cannot say that the points in C are the singularities of z bar. Okay. No point in C is a singular point of f of z is equals to z bar. But the function is not analytic in C. Okay. So the singularities are two types. One is isolated singularities, and another one is non-isolated. So the isolated singularities are again three types. One is removable singularity. Next one is pole. Okay, pole or pole of order k. And third one is essential singularity. Okay. Now, I think in one of the lectures, Dr. Sudesh Kumar Sahu discussed what do you mean by removable singularities and poles. So at least I will give some examples and then I will continue my lecture. Okay. So if you take, there are two ways to classify the singularities, whether the singularity is a removable singularity or a pole or essential singularity, in terms of the limit concept and in terms of the Lorentz series expansion in the deleted neighborhood of that point. Okay. So Z naught is removable singularity if limit z goes to z naught, f of z exists. Then we say that removable singularity of f of z. And we say that a z naught is a pole of order k. Z naught is called pole of order k of f of z if limit z goes to z naught into z minus z naught whole to the power of k into f of z. This quantity exists. Say this quantity called a. This a is not equals to 0 and not equals to infinity. So that means this limit exists and that limit is not equals to 0 and infinity. Then we say that z naught is a pole of order k for f of z. The third case is z naught is called an essential singularity an essential singularity if limit z goes to z naught, f of z does not exist. That means this z naught is neither a pole nor a removable singularity. Okay, the essential singularity means that singularity is neither a removable singularity nor a pole. Okay, in other words, z naught is essential, and so I'm talking all these singularities are the isolated singularities. Okay, z naught is an isolated essential singularity if it is neither a removable singularity nor a pole. That means it's pole of order something. Okay. So if we take an example, we have seen that if you take an example, f of z is equals to z plus 1 if z not equals to 0, and we give 3 if z is equals to 0. Okay. So clearly even this function is not continuous. Okay. But if I define f of 0 equals to 2, okay, then this function is, the limit exists. Okay. So by redefining the function, okay, so if you redefine the function as z plus 1 if z not equals to 0 and 2 if z is equals to 0, then z is equals to 0 is a removable singularity. Similarly, if you take my f of z is sin z by z, okay. So
Sir,
here,
sir,
yeah,
I have a doubt, sir. Sir, can you explain it once more, sir?
Sir,
okay.
f of z at 0 it should be 1.
Yeah, it should be 1, right, sir? G of z.
Yeah, I'm sorry. This is 1. Yeah, I'm sorry. This is 1. Okay.
Thank you, sir.
That's
Thank
true.
you.
That's true. That's true. So f of z is equal to sin by z, sin z by z. Okay. Now, as limit z goes to 0, sin z by z, this is equals to 1. Therefore, your z is equals to 0 is a removable singularity. Okay. Now, if we take another function f of z equals to sine 1 by z, z not equals to 0, okay, we can prove that limit z goes to 0, sine 1 by z does not exist. One can find out two different paths. Okay. So I think this problem is covered in the tutorial sheet. Okay. One can take 1 over n pi. Okay. And zn and another sequence zn tilde is nothing but 1 by 2n plus 1 into pi by 2, where your n belongs to z. And both the sequences converges to 0. Okay. But your f of z, if you take sine 1 by zn, okay. So what is f of zn? What is its value?
One or 0, sir?
Sine n pi.
Sorry, 0, 0, 0.
So f of zn tilde, how much its value?
That is 1.
1 or minus 1 to the power of n.
Yeah, minus 1 to the power of n. Right, sir.
Okay. So we get two different sequences which converges to 0. Okay. But its values are not same. Therefore, limit does not exist. Therefore, limit z goes to 0, sine 1 by z does not exist. Okay. So therefore, z is equals to 0 is an isolated essential singularity. Okay. So if we take the Lorentz series expansion of a function in a deleted neighborhood of that point, if the Lorentz series expansion doesn't contain a principal part, then there is no singularities. If the principal part contains finite number of terms in the deleted neighborhood of that point, then it has a pole. In the deleted neighborhood of that point, if the principal part contains infinitely many terms, it has essential singularity. And indeed, if there is no principal part, means such a point is called removable singularity. So these are the things we have studied, right? In the previous classes, these are the concepts we have studied. So now, let me state a very important theorem called Riemann theorem. Suppose that f of z has an isolated singularity at z is equals to z naught and is bounded in some deleted neighborhood of z naught. Okay, then we can make this function an analytic at the point z naught. Okay, that's what it says. Okay. Then f of z can be defined at z naught in such a way as to be analytic at z naught. Okay. So what is given? Given that our z naught is an isolated singularity for a function f of z, and the function is bounded in some deleted neighborhood of z naught, then we can make this function analytic at this point z naught. This is what Riemann's theorem says. Okay. The proof is simple. So since z is equals to z naught is a singularity, there exists r greater than 0 such that f of z is analytic in a punctured disk with mod z minus z naught less than r. Okay, so we can always find out a punctured disk, okay, where the function is analytic. Now, let me draw the picture. Say this is a z naught. Now, okay, so say this is r. Okay, so here the function is analytic. Okay, in the deleted neighborhood of this z naught, the function is analytic. Now take a point z1. Given a point z1 inside the disk, and choose an r greater than 0 so that 0 less than r less than mod z1 minus z naught less than r. Okay, so what we are doing, we are taking another disk with radius small r. Okay, our z1 is here. Okay, now the function is analytic in the annulus okay, and bounded by the two curves, okay. So I will take this curve in the anti-clockwise direction and this curve in a clockwise direction. Okay. Then the function f of z is analytic in an annulus bounded by two curves say C1. The C1 is nothing but mod z minus z naught equals to small r, and the curve C is nothing but mod z minus z naught equals to capital R. So this, the curve I am calling C, this I am calling as a C1. Okay. Now, what is the a tool which can we use here? We can always use the Cauchy integral formula, okay, at the point Z1. By Cauchy integral formula, our f of Z1 is nothing but, okay, so I'm using for multiply connected domain, Cauchy integral formula for multiply connected domain I'm using. So your f of Z1 is nothing but 1 by 2 pi I integral over C f of j by j minus z1 into dj minus 1 by 2 pi I integral over C1 our f of j by j minus z1 into dz. This I will call as a 1. So this integral I will call as integral I1 plus integral I2. So this I am calling as I1 and this integral I am calling as I2. Okay. Now our aim is to prove that this I2 is 0. Okay. If you prove this I2 is 0, then your f of z1 is nothing but 1 over 2 pi integral over c f of j by j minus z1 into dz. Okay. So our claim is I2 equals to 0. Okay. That means we have to prove that the absolute value of this integral is 0. Okay. So since f is bounded in the disk mod z1 minus z0 less than equals to r, okay, there exists m greater than 0 such that your modulus of f of z is less than equals to m. Okay. Now let us take the integral absolute value of I2. This is same as absolute value of 1 over 2 pi I integral over C1. Okay, this is for all z in the disk mod z minus z0 less than equals to r. So this is nothing but your f of j by j minus z1 into dj. Now, if you take this absolute value inside the integral, that means I'm using the ML inequality. This is 1 by 2 pi integral over C1 modulus of f of j by modulus of j minus z1 into mod dz. Now our f is bounded by m. Therefore, this can be written into m by 2 pi integral over C1 1 by mod j minus z1 into mod dz. Now our aim is to find out the upper bound for this 1 by mod j minus z1. That means we want to find out the lower bound for absolute value of j minus z1. Okay. So what we do, note that. So modulus of j minus z1. Can I write this one as absolute value of j minus z1 plus J minus Z0 plus Z0 minus Z1. So if I apply the second triangle inequality, I can always write this one modulus of Z0 minus Z1 minus J minus Z0. So what is our C? Our our C1 is nothing but mod Z minus Z0 equals to R. Therefore, this can be written into mod Z0 minus Z1 minus R. Okay. Therefore, if I take the reciprocal, so 1 by modulus of J minus Z1 is less than equals to 1 by modulus of Z0 minus Z1 minus R. So I want to apply this at this inequality. So let me call this is 1 and 2. From 1 and 2, so what we can write is integral modulus of I2 is less than or equals to m by 2 pi integral, okay, mod dz by modulus of Z1 minus Z0 minus R. So this quantity I will take it out. So this is same as m by 2 pi into modulus of Z1 minus Z0 minus R integral over C1, okay, mod dz. So this is nothing but the length of the curve. So this is nothing but m into 2 pi R by 2 pi into mod Z1 minus Z0 minus R. Now as R goes to 0, this goes to 0. Therefore, from this, what we can write that our f of Z1 is nothing but 1 by 2 pi I integral over C f of J by J minus Z1 into dz. Okay. So from 1, we have f of Z1 equals to 1 by 2 pi I times integral over C f of J by J minus Z1 into dz. Okay. Now this Z1 is an arbitrary point in this annulus. Okay. Our Z1 is an arbitrary point in the annulus. So we can write that since Z1 is arbitrary, your f of Z is nothing but 1 by 2 pi I integral over C f of J by J minus Z into dz. Okay. So, in particular, this is valid for all Z in 0 less than mod Z minus Z0 less than R. Okay. So, can I say this is an analytic function? Does it represent an analytic function?
Yes, sir.
Yeah, because if f is analytic inside that disk, okay, and if you take any simple closed curve inside, and one can write that your f power n of Z0 is nothing but n factorial by 2 pi I integral over C f of J by J minus Z0 whole power n plus 1 into dz. That means if f is analytic, okay, in a simply connected domain where C is any simple closed curve, okay, which lies inside the domain, then f is differentiable Okay, all derivatives of f exist, and the derivatives can be written in this way. Okay, this is called generalized Cauchy's integral formula. So by generalized Cauchy's integral formula, this represents an analytic function inside the disk mod z minus z naught less than r. Okay. So let me call this is 3. 3 represents an analytic function in mod z minus z naught less than r, okay, by generalized Cauchy's integral formula. Okay, therefore, hence by defining your f of z naught, in particular at the point z naught, okay, is 1 by 2 pi I integral over c your f of j by j minus z naught into dj. Okay, so this function is an analytic function. Okay, so f of z becomes analytic. Okay, in mod z minus z naught less than r. So this Riemann's theorem has a lot of applications. Okay, so one such application is okay. Is this clear? The result is clear.
Sir,
Yeah.
sir, we have shown that integral I2 is 0.
Yes.
In the same way, integral I1, you can say integral I1 is also 0. Not
No, you cannot prove it.
why
You
is
cannot
that?
prove it. Okay.
Because I1 has similar term like I2.
No, 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 no. So to prove I1 is 0, what you need to prove? Then it means that, okay, whatever the function you take, you will prove that this integral is 0. Okay. So what we are saying that, see, where is your R1? Your R0, yeah, yeah. This is your R. Am I right?
Yes, sir, yes.
So your small r you are making to 0. So can in the similar way, can you make that capital R goes to 0? Because that is an isolated singularity. Therefore, there exists a neighborhood. In that neighborhood, the function is analytic. Okay. We need a neighborhood. In that neighborhood, the function is analytic. Okay. Therefore, you cannot take your capital R goes to 0. Is it clear?
Not only that, also we cannot show that if mod of fz is bounded.
Yeah, yeah. That's true. Okay. Because you have taken a deleted neighborhood, in that deleted neighborhood, you are just saying that it's a bounded. Okay, now I want to show the application of this result, okay, for the essential singularity, isolated essential singularity, okay. So again, let me recall the essential singularity means the limit at that point does not exist. Therefore, the behavior of the function at isolated singularity is most of the time it's very surprising. Okay, so the behavior of a function at an isolated essential singularity is sometimes surprising. So, for example, we have a very well-known result called Kesaratrovstras Theorem. That Kesaratrovstras Theorem says that if f has an essential singularity at a point z0, then f comes arbitrarily close to every complex number in the deleted neighborhood of z0. Okay, so let me state the result, and we will prove that. Kesaratrovstras Theorem. If f of z has an essential singularity at z is equals to z0, then f of z comes arbitrarily close to every complex number. So, where in each deleted neighborhood of that point, in each deleted neighborhood of z0. Okay. So, so let us take z0 is an essential singularity. So we can find out a deleted neighborhood of that point. In the deleted neighborhood, the function is analytic, right? So let z0 be an essential singularity of f of z. Then f of z is analytic in throughout the deleted neighborhood. Then f of z is analytic throughout in a deleted neighborhood of z0. So on contrary, suppose f of z is not coming close to every complex number. That means there exists a complex number for which the f is not coming very close. Okay, then we will prove that okay such thing cannot happen. Okay, suppose for some complex number, our modulus of f of z minus a is greater than or equals to epsilon. Epsilon is strictly greater than 0. For all z in the punctured disk, mod z minus z0 less than delta. Okay, in some neighborhood. Okay, for all z in some neighborhood, f is not coming close to a. This is the meaning. Okay, for all z in a deleted neighborhood of z0, f of z is not coming close to a. Okay. So let us define g of z as 1 by f of z minus a. So clearly g of z is defined because the denominator is not equals to 0. Since f is analytic, g is analytic. Okay. So clearly g is analytic. Okay. And modulus of your g of z is nothing but modulus of 1 over f of z minus a, and this is less than or equals to 1 by epsilon. So this happens in the deleted neighborhood of or z0. Okay. Now what is given? What we obtained for g? G is an analytic function bounded in a deleted neighborhood of that point. Okay. So by Riemann's theorem, G of Z has a removable singularity at Z0. Okay. So now we write our G of Z as 1 by f of z minus a. Okay. So since this is an analytic function, so I will write this one as a0 plus a1 into z minus z0 plus a2 into z minus z0 whole square, and so on. So now let us note that limit z goes to z0, our g of z is the same as limit z goes to z0, or 1 by f of z minus a. So what is its value? Limit z goes to z0, 1 by f of z minus a, what is its value? A0, right? Very good. Okay. Now there are two cases. If A0 is not equals to 0, okay, we do not know whether A0 could be 0 or A0 may not be 0 also. Okay, if A0 is not equals to 0, then limit z goes to z0. Okay, so f of z minus a is same as 1 by a0. So this implies limit z goes to z0, our f of z is how much? A plus 1 by a0. So this is a finite quantity. Am I right? This is finite. So that means limit z goes to z0, f of z is a finite quantity. What does it mean? My z0 is what kind of singularity?
Removable singularity.
Very good. F of z has removable singularity at z0. Okay. So case, that means when we assumed that our a0 is not equal to 0, we obtained that the nature of the singularity is removable singularity. Case 2, if a0 equals to 0, that means what? Your a0 is nothing but f of z0, right? That is f of z0 equals to a0 equals to 0. So suppose our ak is the first leading term which is non-zero. Okay, in the Taylor coefficient, in the Taylor series of expansion of f of z. Okay, if ak is the first non-zero quantity, okay, then I can write that 1 by f of z minus a can be written as ak into z minus z0 whole to the power of k plus ak plus 1 into z minus z0 whole to the power of k plus 1, and so on. Okay. So this implies 1 by f of z minus a. If I take z minus z0 whole to the power of k common here, so what we are obtaining? Ak plus ak plus 1 into z minus z0, and so on. So this implies 1 by f of z minus a into z minus z naught whole to the power of k, and if I apply a limit, z goes to z naught. What is its value? I'm taking this
AK. AK.
AK.
Very good, AK. Okay. This implies limit z goes to z naught, your f of z minus a, okay, maybe I will write in it, z minus z naught whole power k into f of z minus a. So this value is ak, and we have taken that ak is the first non-zero coefficient. Okay, therefore this value is not equals to 0. So therefore, what kind of singularity my z naught is?
Pole.
Very good. Therefore,
1 by AK, right, sir?
yeah,
It's 1
please.
by AK. 1 by AK last.
Yeah, 1 by k. Very good. So this is nothing but 1 by k, 1 by ak, which is not equals to 0. Therefore, f of z has a pole of order k at z naught. Okay. Therefore, when we have taken our a naught is not equals to 0, we got the removable singularity. And if we assume that if a naught equals to 0, we got that our z naught is nothing but pole of order k. But what is our hypothesis? Our hypothesis says that z naught is an essential singularity. If z naught is an essential singularity, it cannot be a removable singularity, or it cannot be a pole of order something, right? So this gives a contradiction to our assumption, our hypothesis that z naught is an essential singularity. Okay. So why we got such a contradiction? Because we assumed that for some complex number, f of z is not coming close to a in every deleted neighborhood of z naught. Okay. So this assumption what we have taken, this is wrong. Okay.
Sir, please repeat the case 2 when a0 is equal to 0, that point.
Pardon?
Yes, sir. So please repeat the second case when a0 is equal to 0. Then
So
fz0
suppose,
is equal to 1.
yeah,
This point.
yeah. Suppose
Just one line.
a naught equals to 0. A naught equals to 0. Okay. So
Yes,
suppose let us assume that your ak is the first coefficient in the Taylor's expansion. It is non-zero. That means your a naught is 0, a1 is 0, a2 is 0, and ak minus 1 is 0. Please mute
okay,
your
sir.
mic.
Clear, sir. Okay. It's fine, sir.
Okay.
Thank you.
So,
Yes,
so
thank
in
you.
that case, we got a pole of order k. Okay. Okay. that is we proved z naught is a removable singularity when a equals to a not equals to 0 and z naught is a pole of order k when a naught equals to 0. Okay. So which gives a contradiction that our z naught is an essential singularity. Okay. Which is a contradiction. To our hypothesis that Z0 is an essential singularity of f of z. Therefore, so I will call this assumption. So I will call this one as a star. Therefore, our supposition star is not correct. Okay. Hence, star cannot be true. Okay. This completes the proof. Okay. So there is a nice corollary to the Kesaratrovstras theorem. Okay. So a corollary to this. Suppose f of z has an essential singularity at z is equals to z0. So given any complex number a, then or given any complex number a, there exists a sequence Zn such that Zn converges to Z0 and our f of Zn converges to U. Okay. So it's a very simple. Okay. So what it says that if f has an essential singularity at Z0 for any complex number a, whenever we can always find out a sequence Zn such that when Zn converges to Z0, your f of Zn converges to a. Can someone give the idea of the proof?
Sir,
Yeah.
we can, as we can say contrapositively, that if Zn tends to Z0 and if Zn does not converge to the point A, then then Z0 is not an essential singularity.
Okay.
Like contrapositively, can we say that?
Yeah. But you have a very easy proof. Okay. Just imitate the proof in one line. You will get the Kesaratrovstras. Just apply
Yes, sir.
Kesaratrovstras theorem. Okay. So choose a sequence delta n, okay, for which your delta n's are greater than 0 for all n belongs to n. And limit n tends to infinity, your delta n is equals to 0. Okay. Now, by Kesaratrovstras, because your Z0 is an essential singularity for the function f, okay, by Kesaratrovstras theorem, we can find out a sequence of points Zn such that our f of Zn, modulus of our f of Zn minus a is less than 1 by n, okay, for all points in the deleted neighborhood of Z0. Okay. So your Fn comes close to A by Kesaratrovstras theorem. Okay. What does it mean? This implies your f of Zn converges to 0 as Zn converges to Z0. Okay. Just a simple consequence. So a more general version of this Kesaratrovstras theorem is given by Picard. Okay, so let me state the result. A more general version.
So f of z converges to A.
Yeah, very good. Yeah. Converges to A. Thank you. A more general version of Kesaratrovstras theorem is described by the Picards. So let me write is a Picard's great theorem. So if you take in a neighborhood of an isolated essential singularity, a function assumes every complex number, possibly one exception, infinitely often. Okay, that is called Picard's great theorem. Okay, so in the neighborhood of an essential singularity, an isolated essential singularity, a function assumes each complex number with one possible exception infinitely often. Okay. So for a proof, so I will just leave an exercise. So you can find out in a standard books like let me give E. Heil. So analytic function theory. If somebody is interested, can just go through the proof. Okay. So, but I will give one illustration of this Picard's great theorem. Okay. Let me take f of z is nothing but e power 1 by z. Okay. So z is equals to 0. What kind of singularity for this function f of z?
Essential.
Okay. Z is equals to 0 is an essential singularity for f of z. Okay. So assume that, okay. So we want to prove that it comes, okay, it assumes, okay, in a deleted neighborhood of that point, okay, essential singularity, okay. It assumes every complex number, possibly one exception. Okay. Very good. Okay. So let C is not equals to 0. Okay. Then find out the solution of e power 1 by z is equals to C. Okay. So the solution of e power 1 by z is equals to C is given by, so your 1 by z equals to log of C. Okay. C is a complex number. Okay. So your z is nothing but 1 by log C, and this can be written into 1 by the principal logarithmic c plus 2k pi I, where k belongs to z. Okay, so let us denote this sequence. Your Zn is nothing but 1 by log c plus 2k pi I, where k belongs to z. Okay, so now we are getting an infinitely many. Okay, see, we get a sequence. Okay, in an infinite sequence which comes close to the complex number c. Okay, that is infinitely many Zns are contained in every neighborhood of z is equals to 0. Okay. So far we have studied the singularities at finite number of points. Okay. So now let us discuss the singularity at z is equals to infinity. Okay. So singularities, isolated singularity at z is equals to infinity. Okay. So when do you say that z is equals to infinity is a singularity? So first we have to define what do you mean by z is equals to infinity is a singularity. Okay. So let me give first formal definition. A function f of z has an isolated singularity at z is equals to infinity, and if you take the deleted neighborhood of that infinity, the function is analytic. If f of z is analytic in a deleted neighborhood of infinity. Okay, so now to view this neighborhood of infinity, what we do, we will take the stereographic projection, that Riemann sphere. Okay, so we will assign the north pole 0, 0, 1. Okay, we will identify north pole with infinity. So when we are saying the neighborhood of infinity, means you are taking the neighborhood of this point, north pole. Okay. So let me write what does it mean. That is, there exists a real number R such that f of z is analytic in R less than mod z less than infinity. Okay. So, so what we are saying that for the large value of R, okay, so it's we are taking that in the deleted neighborhood of that infinity, we are saying that the function is analytic. So now to see that, to classify the infinity, the singularity of infinity, so we will see that we will relate this one as, okay, so f of z is analytic for mod z greater than R if and only if f of 1 by z is analytic in where modulus of 1 by z less than 1 by r. Right? So we are taking mod z greater than r. So 1 by mod z is less than 1 by r. So here the function is analytic. Okay. Therefore, if the function has isolated singularity, okay, at infinity means at 0, okay, so it has an isolated singularity. F of 1 over z has an isolated singularity. Okay. So what it means that is, yeah, I'm just coming. Hello.
Z analytic in mod z 1 by mod less than or not 1 by r. So we have to stroke of z only.
Yeah, sorry. So our f of z has an isolated singularity at z is equals to infinity if and only if your f of 1 over z has isolated singularity at z is equals to 0. Suppose for f of 1 by z, if z is equals to 0 is a removable singularity, then z is equals to infinity is a removable singularity for f of z. For f of 1 by z, if z is equals to 0 is a pole of order k, then z is equals to infinity is a pole of order k for f of z. Suppose z is equals to 0 is an essential singularity this, and we can think that z is equals to infinity is an essential singularity for f of z. So what we can write, z is equals to infinity is removable or a pole or an essential singularity of f of z if and only if z is equals to 0 is removable singularity or a pole or an essential singularity so respectively. Okay. So if z is equals to infinity is a removable singularity for f of z, okay, respectively for f of 1 by z. If z is equals to infinity is a removable singularity for f of z, then z is equals to 0 is a removable singularity for f of 1 by z. Okay. Similarly, if z is equals to infinity is a pole for f of z, then z is equals to 0 is a pole for f of 1 by z. Okay. Similarly, for essential singularity. Okay. So let us take one example to see this. So your f1 of z is equals to say z square plus 1. Okay. So f1 of 1 by z is nothing but 1 by z square plus 1. Am I right? So z is equals to 0 is what kind of singularity for f1 of 1 by z?
Pole.
Pole of order 2. Okay, very good. So z is equals to 0 is a pole of order 2 for f1 of 1 by z. So what does it mean? That is, z is equals to infinity is a pole of order 2 for f1 of z. Okay? When z is equals to 0 is a pole of order 2 for f1 of 1 by z, then z is equals to infinity is a pole of order 2 for f1 of z. Okay? So you can see that second example, if you take f2 of z is equals to e power z, okay? So f2 of 1 by z is nothing but e power 1 by z. So what kind of singularity z is equals to 0 for f2 of 1 by z?
Essential.
Okay, z is equals to 0 is an essential singularity. Okay, z is equals to 0 is an essential singularity for f2 of 1 by z. Therefore, z is equals to infinity is an essential singularity for f2 of z. Okay, so now we will see the further study of the singularities at z is equals to infinity. Okay, so let us take a polynomial. If f of z is equals to summation k n equals to 0 to k a n z to the power of n. Okay, this is a polynomial of degree k. Okay, now define your g of z is nothing but f of 1 by z. So this can be written into ak by z to the power of k plus ak minus 1 into by z to the power of k minus 1 and so on, plus a1 by z plus some constant a0. Okay, so if I multiply z to the power of k to your f of 1 by z, what you are getting? This is nothing but your ak plus ak minus 1 into z, ak minus 2 into z square and so on, plus a1 into z to the power of k minus 1 plus a0 into z to the power of k. Okay, so now I want to find out what is my ak. Okay. So if I take limit z goes to 0, z to the power of k, your f of 1 by z, what is its value?
AK.
And since it's a polynomial of degree k, this is not equals to 0. Okay. Therefore, therefore, your f of 1 by z equals to g of z has a pole of order k at z is equals to 0. Therefore, your f of z has a polynomial of degree k at z is equals to infinity. Okay, so hence f of z has a pole of order k at z is equals to infinity. Okay, now we can say that z is equals to infinity is a pole of order k. That means this limit exists. This limit exists, and that limit is not equals to 0 and not equals to infinity. Okay, So in other words, note that the entire function f of z has a pole of order k at z is equal to infinity if and only if limit z goes to infinity, limit z goes to 0, z to the power of k of f of 1 by z, okay, this is same as limit z goes to infinity, okay, your f of z by z to the power of k, okay. So this is some a constant which is not equals to 0 and infinity, okay. So with these, okay, now we have studied what do you mean by singularities and poles and essential singularities and removable singularity and some classification. And now using this, we want to find out the real integrals, okay. Before that, let me state, suppose your f of z is analytic in a deleted neighborhood of z naught, then by Lorentz theorem, we can always write a Lorentz series expansion in the deleted neighborhood of z naught, okay. By Lorentz theorem, we have our f of z is nothing but summation n equals to minus infinity to infinity an into z minus z naught whole to the power of n, okay. This happens in a deleted neighborhood of z minus z naught less than delta, okay. What is my ans? Where our ans are nothing but 1 by 2 pi I times integral over c f of z by z minus z naught whole to the power of n plus 1 into dz, where your n belongs to z. So that means we have some z naught somewhere, okay. So this is z naught, okay. So in the deleted neighborhood of z naught, okay. So take any simple closed contour, okay, in an anti-clockwise direction, okay. So this is what my C is, okay. Here C is a simple closed curve enclosing z naught and contained in the neighborhood. So in particular, if you put n equals to minus 1, so in particular, your a minus 1 is nothing but 1 by 2 pi I integral over c our f of z dz, because n equals to minus 1 gives this quantity is 1, okay. So this is nothing but, okay, this is nothing but integral over c f of z dz equals to 2 pi I times a minus 1. Okay. Now here a minus 1 is called the residue of f of z, okay, at that point. Okay. Here a minus 1 is called the residue of f of z at z naught. And we denote it by the residue of f of z at z naught. Okay. So for example, if you take f of z is equals to e power 1 by z, okay, the residue of f of z at 0 we want to find out, and 0 is an essential singularity, right? Okay. Now if we write this one as 1 plus 1 by z plus 1 by 2 factorial into 1 by z square and so on. Okay. So what is your a minus 1 here?
1.
Very good. So the residue is nothing but 1. Okay. So if we take more generally, if we consider e power 1 by z to the power of k, so this is nothing but 1 plus 1 by z to the power of k plus 1 by 2 factorial into 1 by z to the power of k and so on, right? So if we take C is in a simple closed curve, which is, okay, in the anti-clockwise direction around the point 0, then what is your e power 1 by z to the power of k into dz?
0.
Okay. What is, suppose if k equals to 1, what is its value?
1. 2 pi I. 2 pi.
Okay. So 2 into pi I. Okay. So if k not equals to 1 and k belongs to z, what is its value?
Then 0.
0. So where C is in a simple closed contour, enclosing the origin, which encloses the, which z is equals to 0. Okay. So similarly, one can find out for sine 1 by z square. Okay. So what is the series expansion of this? 1 by z square minus 1 by 3 factorial into 1 by z square whole cube and so on. Right? So this is for mod z greater than 0. Okay. So what is the residue of sine 1 over z square at z is equals to 0? What is its value?
0.
0.
0. Okay. Because 1 over z term, okay, is not appearing in the series. So therefore its value is 0. Okay. Indeed, we can write in more general way, integral over c sine of 1 by z square into dz, okay, as similarly I will write, okay, if k equals to 1, what is the value?
2 pi I.
K equals to 1, okay, 2 pi I. So if k not equals to 1, but k belongs to z, what is the value?
Then 0.
0. Okay. So third one is maybe last one I want to write. For z not equals to 0, okay. So residue of z square into sine 1 by z square at z is equals to 0. What is its value? So I am multiplying z square, okay, to this. So what will be the value?
0, sir.
0.
0. Okay. So I will stop here. Maybe after the break, I will continue in evaluating certain integrals, and then I will state the residue theorem for a finite number of singularities, and if the singularities are finite, and also for the at the point of infinity. That means in the extended complex plane. Okay. So do you have any questions?
Sir, I
Yeah.
stated singularity at infinity. Can you go back there, sir?
Where?
I stated singularity at infinity.
This is?
Yeah, so little bit observe as little observe.
Yeah, in the second talk, we will give more examples on this. Okay.
No, sir.
Uh,
I want to ask one thing, sir. Here.
yeah.
I did not get that point.
Pardon?
Little bit observe. In
Your
the
voice is
definition,
not clear. No,
definition
what I
of
want to no, what I want to say that here. So using the information at z is equals to 0 for f of 1 by z. Okay. So suppose z is equals to 0 is a removable singularity for f of 1 by z. Then z is equals to infinity is a removable singularity for f of z. That's what I want to say.
yes, so that part I got. So little bit observe.
What is that?
Sorry, can you go back little, sir? Just a little.
Okay.
Yeah, sir. In the note that part, sir. Note that fz is analytic for mod implies and implied by mod z 1 by mod z less than r, sir. Is that, sir, less than or greater than? I got
Oh,
confused.
no. See what is there? See, you are having. See, r is a number. Okay. So z is here. That means your mod z greater than r. Okay. Where is 1 over z? Your 1 over z is inside, right? Hello. If z is here, your 1 by z is inside the disk, right? Yeah. So any other questions? So if there are no questions, then we will meet at exactly 6.